Okay, good evening, everybody. I didn't hear you. Okay, this is Professor Ayorinde welcoming you to the first organic chemistry session for the spring 2014 semester. I do hope you guys had a pleasurable New Year celebration, so I want to say Happy New Year to all of you. Okay, we do have a lot of material to cover this semester. We have about 11 chapters to cover. We only have 12 weeks to cover those chapters. So that means we have to do a lot of work. Okay, I have to do a lot of work. You guys have to do a lot of work. So today we are going to start the session. I am not going to spend too much time telling you about the syllabus. The syllabus is already posted in Blackboard. It is your responsibility to know exactly what is in the syllabus. So we do not want to waste our time here just discussing the syllabus. But I do want to let you know that the first homework assignment, which is our Chapter 14, end of Chapter 14 questions, will be posted tomorrow, and that will be due on Sunday at 11 p.m. That is Chapter 14 hour, end of Chapter 14 questions, due on Sunday at 11 p.m. Okay. I also do want to let you know once in a while before the exams, we are going to have online review sessions. And for those sessions, I will be sending you a link so that you can join me during those sessions. And also, most of the webcasts for the previous lectures that I gave in previous years, they have been posted in YouTube, and some of them have been posted in Blackboard. So I do advise that you take advantage of those resources. Make sure take a look at them before you come to class. So that when you come here, you are able to make a meaningful contribution to this session, okay? So right away, we are going to start our session. Of course, I do advise that if you have any problem with the syllabus, you want to ask questions, come and see me in the office. Most of you know where my office is. And those of you who do not know where my office is are listed in the syllabus. Okay, today we are going to start Chapter 14. Okay, taking from the 8th edition of McMurray, Chapter 14, you will be surprised, does contain a lot of material that you guys have already done in the Organic 1. So most of the chemistry is not new to you. Maybe a few of them will be new. So therefore, Chapter 14 should be a review to some of you. So in Chapter 14, we are going to discuss the chemistry of conjugated alkenes. Specifically, we are going to discuss electrophilic addition reactions of conjugated alkenes. And finally, we shall discuss the chemistry of the conjugated alkenes, including the Diels-Alder cycloaddition reactions. Now, on the next slide, I have what I call a list of learning outcome objectives. In other words, upon completion of this chapter, you should be able to perform all of the activities on this slide here. For example, you should be able to identify conjugated alkenes and conjugated molecules. You should be able to write mechanism for electrophilic addition reactions. So therefore, what I want you to do is to use this list of learning outcome objectives as a study guide for the preparation of all of the quizzes and the examination that we are going to take for this chapter. Okay? So I do advise that you come back to this list, keep asking yourself, Do you have competency in each one of these items here? If you say no, then that means you either have to go back and review your note, your textbook, the webcast, or even come and see me in my office. I really do advise that most of you should come and see me in my office. If you're having problem much earlier on, it's better to see me earlier than at the end of the semester. So at this point, the question is, what are conjugated alkenes? Conjugated alkenes are what we call organic molecules that contain alternating single and double bonds. Organic molecules that contain alternating single and double bonds. For example, you take a look at this molecule here, isoprene. You have a double bond here, and you have another double bond here. Now, separating those two double bonds is one single bond. So therefore, we say this is a conjugated alkene. The same thing in this molecule here, 1,3-cyclohexadiene. Most of this we did last semester, so the nomenclature should be familiar to all of you. We have a double bond here, another double bond here. Both of those double bonds are separated by one single bond. So therefore, we say this is a conjugated alkene, diene. In this particular case, you have two double bonds. Now, this molecule here we call carotene. How many of you eat carrots? Okay, this is what you eat when you eat carrot. Okay. Okay, the orange color that you see in color, this is carrot. This is what gives carrot the orange color. Indeed, most material, natural material, food material that you have in nature that have orange color, this is the molecule that gives that color. And you can see here, it's a molecule that contains alternating single and double bonds. Double bond here, separated by a single bond. You see the alternation here. Now, many of you will wonder, why do we want to study these molecules? Okay, you'll find that these molecules actually give us an insight into many of the reaction mechanisms that we do in organic chemistry. Okay, as a result of studying this molecule, we also are able to have an idea what is the effect of temperature on chemical reactions. Some of those we are going to do today. For example, let us look at the evidence for this type of molecules existing and being very unique indeed. Unique because we say they are very, very stable molecules compared to other alkene molecules that are not conjugated. Okay. Than other alkenes that are not conjugated. Now let us look at the evidence for this stability. Why do we say these molecules are more stable than those molecules that are not conjugated? Start by saying evidence for relative stability of conjugated alkenes. Let us take a look, for example, this molecule here. This is 1-butene. If we perform hydrogenation on this molecule, all of you already know what hydrogenation is. If we perform hydrogenation on this molecule, using hydrogen and some kind of catalyst, let's use platinum. We get this molecule here. In which we have added 2 hydrogen atoms across the carbon-carbon double bond. Okay, now we no longer have the double bond in the product. Now we have butane. If we take a look at the heat of hydrogenation or the heat of reaction for this reaction, delta H, hydrogenation, we find that it is minus 126 kilojoules per mole. Minus 126 kilojoules per mole. All of that, what does that tell us? It simply tells us that this carbon-carbon double bond here, when we made it, we actually embedded 126 kilocalories of moles heat inside that double bond. And so when you remove the double bond, it releases the heat. Now, if we go by this evidence here, then we'll say anytime we have a carbon-carbon double bond and we do hydrogenation, we should be able to get minus 126 kilojoules of heat release. If you have 2, then it should be times 2. If you have 3, it should be times 3. For example, supposing we have this. One 3-pentadiene. We do hydrogenation. Now, if our assumption is right, what do you think the heat of hydrogenation of this molecule will be if you remove both of the double bonds? What should it be? What should it be? Somebody say 252 exactly. Thank you. Okay, 252 kilojoules per mole. Okay, in other words, we are going to get this. The expected, expected delta H hydrogenation for this, you guys told us it should be minus 252 kilojoules per mole. Indeed, the actual heat of hydrogenation for this reaction is minus 252 kilojoules per mole. So our assumption is mostly right. So if you have 3 double bonds that are not conjugated, therefore, we will expect that we keep adding we could predict the amount of heat that will be generated. Now, supposing now we take this molecule here. Look at this here. Let me take that back. This is here. This is supposed to be, this double bond was supposed to be here. Okay. If you take a look at this here, this will be 1,4-pentadiene. Sorry about that. 1,4-pentadiene. If you take a look at this, this is not a conjugated molecule. This is not a conjugated molecule. Because what you have here, you have a double bond here, single bond, single bond. You have two single bonds separating the two double bonds. So therefore, this here is not conjugated. Okay. Okay. Now let us now take a look at this. Supposing we now take this. This is 1,3 butadiene. As you can see here, this is a conjugated molecule. Double bond, single bond, double bond. You have alternating double and single bonds. Now we perform hydrogenation on this molecule here. We get this. Get butane. Now the heat of hydrogenation for this reaction, delta H hydrogenation, for this reaction happens to be minus 236 kilojoules per mole. So what do we have here? Take a look at one butene has only one double bond, right? We do hydrogenation, we release 126 kilojoules of energy. And then we take this one here, the butadiene, which is conjugated. What we normally will expect is that we expect minus 252 kilojoules of the heat of hydrogenation should be minus 252, but it is not. It's minus 236. So what is the difference? What is the difference? So we have 2 minus 252 minus 236, and so we have here 16 kilojoules per mole. So compared to what we normally expect for the heat of hydrogenation of this here, what we therefore have to say is this molecule is unusually stable as a result of the conjugation. Because if you look at this here, the 1,4-pentadiene, which was not conjugated, you did the hydrogenation, you get what was expected, minus 252. And here, we do the hydrogenation, we get minus 236, telling us that these double bonds here, they have less heat embedded in those double bonds. Okay, whenever you have a system, the less energy you have in that system, the more stable that system is. Okay, and that is what you have here. In other words, this double bond contains less energy within them. So when you release the energy that you have is what they contain originally. So what this is telling us, the conjugated system, therefore, is more stable than the non-conjugated system. Okay, do you follow that so far? Okay. Now, the question now is, why are conjugated alkenes, why should they be more stable than the non-conjugated alkenes? Why are conjugated alkenes more stable than non-conjugated alkenes? To answer that question, we need to take a look at the orbital picture of the conjugated alkenes. Once again, let us go back to 1,3-butadiene. We have this here. Let us take a look at the orbital picture of this molecule. 1,3-butadiene. If you look at this molecule here, each one of the single bond here, this here, all of this here, all of this here, these are what we call sigma bonds. This is a sigma bond. This here is a sigma bond. All of the single bonds are sigma bonds. And each one of the double bonds is a mixture of sigma bonds and pi bonds. As you all know, we represent pi with the Greek symbol pi, and the sigma we represent with this signal here, symbol here. So in the double bond, we have a pi bond and a sigma bond. And each one of the single bonds here is a sigma bond. Okay. Now, let us take a look at the orbital picture. So we have carbon bonded to carbon, bonded to carbon, and each one of these we say is a sigma bond. It's a sigma bond. So what we have here, we have the skeletal structure for this molecule. Now, because of this double bond here, we also know that the hybridization for this carbon here, this is an sp2 hybridized carbon. This is also an sp2 hybridized carbon. The same thing here, and the same thing here. And for each one of those sp2 hybridized carbon, we know we must have a p orbital, right? Okay, so therefore, we have a p orbital here, another p orbital here, another p orbital here, another p orbital here. We also know that each one of those p orbitals contain one electron. One electron, 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 electron. Now, in order to satisfy the tetravalency of carbon, because carbon needs 4 bonds, this p orbital here and this p orbital here, they will overlap, and as such, those 2 electrons within the 2 p orbitals, they will be in the overlap orbitals. So therefore, let us represent the overlap by saying this here is overlapping with that. So those 2 electrons will be within the overlap orbitals. The same thing here, these two here, there is a side-to-side overlap. If you recall what we did last semester, for each pi bond, there is a side-to-side overlap of the p orbitals. It's a side-to-side overlap of p orbital. That makes up your pi bond. Okay? So now, each one of these side-to-side overlap here constitute our p orbital. And that is the p orbital, and I'm sorry, the pi bond that you see here, right here. The same overlap of this p orbital and this p orbital from this pi bond here. Now, supposing we have this. Instead of this p orbital here and this p orbital here overlapping, supposing we have a situation in which this electron here simply goes to this p orbital here, right? Goes to this p orbital here. Let us do that. Okay? I draw this again. Okay, no, sorry, let me use my green pen so I don't confuse you. Okay? Let us imagine that instead of these two electrons here residing in the overlap orbital, they simply just come to this p orbital here, right? What is going to happen? We now have those electrons are just now here, because those electrons could simply just move, right? Now, these two structures now would be what we call resonance structures. So all we've done now is simply just to move the electron from one orbital to another orbital. They are not, these two electrons are not being shared at this point, right? Okay, so let us write what this would look like. Right now, let me take care of this here. Keep in mind this structure that we have here, this here looks like this. This is what we have right here. Okay, this is this structure here. Now let us now draw this structure on this side, the one we call the resonance structure. What will it look like? Okay? Keep in mind now we have these two electrons here now. Okay? We still have the double bond here. Okay, that is what we have here. Okay, so therefore, these two are resonance structures. You guys should be familiar with resonance structures at this point. Can anybody tell me the structure that I've done here in order to complete this structure? What is wrong with this structure? What is, yes? Formal charges, exactly. There must be formal charges here. Okay, where will be where are you going to have the formal charges? Let me number this carbon here so that you could help me out. So this is carbon 1. Let's say this is 2, this is 3, this is 4. Where are the formal charges? Oh, a positive charge on carbon 2, very good, excellent. Exactly. Okay, we did that last semester. So the formal charges will be on carbon number 1 and carbon number 2. So what have we done here? All we simply done is to move electrons. Okay? Okay. The convention that we do for we use for doing that, simply just do this. We draw an arrow to show that this electron, these 2 electrons here, they are moving to this carbon here. That is what we normally do. And therefore we get a resonance structure. Okay? Now, we could now draw additional resonance structures. Can anybody tell us what additional resonance structure can we get and what electrons can we move between what carbon and what carbon? Keep in mind that each one of these, this here has nothing here, this here has nothing, this one has electron, but it is being shared as a result of overlap here. Okay? Any other resonance structures? Use the numbers, yes. This is carbon 1 here. Let me help you out here. This is carbon 1 right here, carbon 2, carbon 3, and carbon 4. Okay, yes. Any idea? Yeah, go ahead. Exactly. Move the double bond from between carbon 3 and 4. Okay, move it to between 2 and 3. Because this orbital here, at this point, don't forget this orbital here is vacant. There is nothing here. So you could move these 2 here, right? Therefore, we could move these 2 here. Okay, and what do we get? Get another resonance structure, right? And that resonance structure will look like this. Now we have a double bond here, right? Okay, no, this is still a single bond. Double bond here. Right here. And now what is going to happen to carbon number 4? What is going to happen to carbon number 4? Keep in mind we still have this here. What is going to happen to carbon number 4? Formal charge? Exactly. So now since we move this, keep in mind each one of these line here, this bond here, represent 2 bonding electrons, okay, which will be this here. So what we've done here is simply just move this here to here, okay, and that is what we've done here. And therefore, that means carbon number 4 now has a formal charge of +1. The point is, when you have a conjugated system, those pi electrons are delocalized delocalization of pi electrons, okay, result in the stability of conjugated alkenes. result in the stability in the relative stability. Let me make myself some room here. Okay, delocalization this pen is moving too fast today. Delocalization of pi electrons result in the stabilization of conjugated alkenes. And that localization is essentially what is referred to as resonance. So the reason why these molecules are stable is because those electrons, they are delocalized over the chain of atoms that make up the conjugated system. So therefore, in order for you to have a conjugated alkene system, to have a conjugated alkene, the molecule must contain a chain of atoms, that have one or two p orbitals. Okay. In order for you to say a molecule is conjugated, you must have a chain of atoms in which atoms within that chain must have one or two p orbitals. Because that is the only way you will be able to write resonance that involves all of those atoms, thereby making them more stable, very stable. So therefore, if I give you this molecule here, supposing I give you this molecule here, let me help you out here. Let me number this. So this is carbon 1, carbon 2, carbon 3, carbon 4, 5, and 6. Can anybody tell me which of the atoms in this molecule are involved in conjugation? Which of the atoms? Yes. 1, 2, exactly. 1, 2, 3, and 4. Very good. Okay, how about 5? Why is 5 not involved in the conjugation? It has no p orbital. Excellent. Because if you take a look at 5 and 6, what is the hybridization of carbon 5? sp3, exactly. sp3 carbon. The same thing for carbon 6, sp3 carbon. sp3 carbon do not have p orbitals, and as such, they cannot be involved in conjugation. Okay. Okay, so at this point, I want to now shift gear a little bit and now begin to go to the reactions of conjugated system. What is the consequence of some of these things that we have been discussing? We have resonance. Is there a consequence to that? Okay? Okay, so let us start with the reactions of these systems. We start with what we call electrophilic, addition reactions of conjugated alkenes if you recall, supposing if we take this molecule here, go back to our butene molecule. If you take that molecule and we want to perform electrophilic addition using, in this case, hydrogen bromide with this molecule. Okay, let me go ahead and number this to help you out. So this is carbon 1, carbon 2, carbon 3, carbon 4. I'm sorry, let me say this. I don't mean to put a double bond here yet. This is 2, and this is 3. Okay. We want to do electrophilic addition to this carbon-carbon double bond. Where will the hydrogen go? Which carbon will the hydrogen go to? Carbon 1? Okay, very good. Okay. And therefore the bromine will go to carbon 2, right? Okay. Let's use a different color pen to show. So the hydrogen goes to that carbon. So that means the bromine goes to carbon number 2, just as you said. Bromine goes here. Now this type of addition, we call this a 1,2 addition reaction. A 1,2 addition reaction. Now, if we now introduce conjugation in this system, let us now take a look at this one here. Now, this first reaction here is what we did last semester. Just a regular electrophilic addition reaction. Okay? You look at the regiochemistry for this, we say this is a Markovnikov addition reaction, right? We say this is a Markovnikov addition reaction. Markovnikov addition meaning that the hydrogen goes to the carbon that contains more hydrogen, in this case this one here, right? And the bromine goes to the carbon that contains less hydrogen, in this case this one here. So this is a Markovnikov addition of hydrogen bromide. Now, once we now have the conjugated system, we are going to get a series of products. Okay? We will get this product here. I do the 8BR again. We'll get this. We get what we call a 1,4 addition. One-four addition product. Now, supposing I ask you to give me the mechanism for this reaction. Supposing I ask you to give me the mechanism for this reaction. What do you think that would be? Okay? Let's start. Okay, let me go to a new page. So we have this. That is the 4 addition product. Mechanism. What is the reaction mechanism? Okay, anybody want to give this a try? Keep in mind, we are adding the hydrogen to carbon. This is carbon 1, carbon 2, carbon 3, and carbon 4. We are adding hydrogen. Hydrogen is added here, and then bromine is added to carbon number 5. How did that happen? Based on what we have been discussing so far, how did that happen? Okay, very good. So that the first thing that, but what is the first thing that happens though? Okay, this pi electron will attack the protons, right? Okay, because in the electrophilic addition reaction, this here will be your nucleophile, the pi electron here, and the proton will be your electrophile looking for electron. Okay, so let us change its color so that I use a different color. Okay, so the first thing that happens, take this out of the way. This pi electron here comes here to grab that proton and thereby breaking the hydrogen bromine bond. And so what you have, you now have this. Hydrogen is here attached to carbon number 1. And now the pi electron is gone, so this carbon here now becomes a positively charged carbon, carbocation. Now we have this. So now we have what we call allylic carbocation. Okay? Allylic because this carbon here is attached to a carbon-carbon double bond. The carbon that is attached to a carbon-carbon double bond is referred to as an allylic carbon. So now we have an allylic carbocation. Okay? In so doing, we also have the bromine is still here, right? The bromine that we release here is still here. So how do we get this product? That's what we ask you to do, to give the mechanism. How do we get to here? The resonance, right? Exactly. We now write the resonance for the intermediate carbocation. So this pi electron will move here. Okay? So if you then do that, you now get this resonance structure. You can now see the consequence of resonance, electron delocalization, when it comes to chemical reaction relating to the conjugated system. So now what do we have? We now have this. We now have this here. Now the positive charge is on that carbon. Now what happens now? What happens now? What is the next thing that happens? The bromine now acts as a nucleophile. Okay, a nucleophile is something looking for a positive center. So now acts as a nucleophile. Now attach this carbon here, and that's how we get to here. Okay, and so that's how we go to the 1,4 addition product. This is your 1,4 addition product. Is it possible to get the 1,2 addition product? Is it possible? Is it? Why not? Is it possible for this bromine here to attack this carbon? It is possible. All right? Before you draw the resonance, this bromine could also attack this carbon. Now, if it does that, if the bromine attacks that carbon, you could also now get the 1,2 addition product. So in this case, we now get the 1,2 addition product. Yeah, that is possible. So therefore, in the case of the conjugated system, generally you get two types of product. You get the 1,2 addition product as a result of the reaction between the initial carbocation and your nucleophile. In this case, the nucleophile is the bromine, and this is your initial carbocation. That initial carbocation will undergo resonance to give you this here, that gives you the 1,4 addition product. But the initial carbocation gives you the 1,2 addition product. And in an exam, I will give you these two products here and say, give me the reaction mechanism. How did this reaction occur? This is the kind of thing I want you to do. Okay. Okay, you have a question? Oh, okay. Anyway, so now here we've shown you the possibilities with the conjugated system. So how much time do we have left? How much time do we have left? 24? Oh, plenty of time. Okay. Okay, so supposing we have this. Supposing we have this. Okay, is this a conjugated system? Yes or no? Yes. Okay. Which are the conjugated carbons here? Say 1, 2, 3, 4, 5, and 6. Which atoms are conjugated here? Which carbon? 1, 2, 3, and 4. Very good. Now, supposing I therefore give you this. Say, give me the product of this reaction. Give me the product of this reaction. Okay. Okay, let's start with where do you expect the hydrogen to go? Just give me the number. Where would the hydrogen go? You say 1. About the bromine? Keep in mind we do expect to get 1 2 addition product and 1 4 addition product. Okay, so the hydrogen could go to 1 and then bromine go to 2. Okay, very good. Keep in mind we have hydrogen here initially, so let us show that. Okay. So we expect the hydrogen to go here. Use a different color. And then you say the bromine will go here, right? Okay. And the double bond is still here. Okay. What kind of product is this? That's the 1 2 addition product. Okay, very good. Okay, what would be the other product? What would be the other product? 1 4, right? Okay, so you expect the hydrogen to be in 1 and the bromine in 4. Okay. Now where would the double bond be? Between 2 and 3. Very good, very good. So we also expect to get okay, this is carbon 1, so we expect this here, hydrogen is here. And we use a green color just to show that. And the bromine we say will be here. The hydrogen that was there before is still there. And now you say the double bond will move to 2 and 3. Very good. Now can you write a mechanism for this? You should be able to. It's the same thing that we just did. It's just a different molecule. Okay? Supposing I say this here, this molecule reacts with hydrogen bromide to give this, and I say give me the reaction mechanism. Those are the kind of questions you get. Okay? Everybody can do that now? Okay, very good. Okay, so now let me also now shift there a little bit. Remember, I told you earlier that we could use the reactions of conjugated system to study the effect of temperature on chemical reactions. Once again, let us say effect of temperature on chemical reactions. In this case, we want to use the reaction between the electrophilic addition reaction of a conjugated diene or conjugated alkene with hydrogen bromide. If we take this, and we take hydrogen bromide, hydrogen bromide. Okay, get this here. Let's see here. If we perform this reaction at 0 degrees, Celsius, very cold, we get this product, the 1,2 addition product. But if we do the same reaction at 40 degrees, then we get the 1,4 addition product. Here we get the 1,2 addition product, and here at 40 degrees we get the 1,4 addition product. In this case, this product here that we do that we obtain at low temperature, in this case 0 degrees, we say this is a kinetic product. And the other product that we obtain at 40 degrees, we say this is a thermodynamic product. This here is a thermodynamic product. And another term we could use for thermodynamic product, we could say equilibrium product. Okay. Now, what is going on here? If we draw the reaction energy profile for these two reactions here, it is so I got some space here. If we draw the reaction energy profile for this, So the reaction energy profile for this for the kinetic product. What happens? This is energy here, and here this is the reaction progress right here. We know that this is an electrophilic addition reaction, and in electrophilic addition reaction you form a carbocation intermediate. That much we know. Okay, so this is what's going to happen. You have to start in a conjugated system here. Assume that it is here somewhere. Let me raise it up a little bit. It goes through the energy of activation, then it forms the intermediate, then it comes to the product. Right here is your carbocation. Let us represent that by positive charge right here. From a carbocation, this is your transition state. Let's say transition state 1 and transition state 2. Okay. Now, if you now have this, keep in mind that what we are doing here, okay, this is, let me say, this is your conjugated system, conjugated alkene. Let's call that conjugated alkene, okay, right here. And this is your product. Now, if you then, on the other hand, let us overlay the reaction energy profile of the 1,4 addition on top of this here. Okay. Since I have more space here, let us use this here. Okay, I start with the green. I will use green for the 1,2 addition. Okay, at this point I want to use red for the 1,4 addition, starting from the same starting material. Okay, notice what we've done here. The 1,2 addition, the energy of activation right here is much lower than the energy of activation for the 1,4 addition reaction. This is the energy of activation for the 1,4. So this is the 1,2 right here, and this is the 1,4. So at lower temperature, at low temperature, at 0 degrees, this reaction only has enough energy, to overcome this energy of activation. And then once it does that, it collapses to get to the product. Even though the product is not as stable as in this case, keep in mind what we have here. This is telling us here, this here, because this is the energy right here. This is telling us here, the product from the 1,4 is more stable than the product from the 1,2. So even though the product from the 1,2 and 1,4 reaction is more stable, because it does not have enough energy, we don't get that product. Okay, so therefore, this reaction, the 1,2 reaction is therefore controlled by the amount of energy you have. So we say that is controlled by kinetic, it's a kinetic control reaction. So we could actually manipulate these reactions to go the way we want it to go, depending on the kind of temperature we use. So therefore, we say this is a thermodynamic product because the thermodynamic product is the most stable product. Okay? That is the product that you obtain as a result of equilibrium condition. Because in this case, if you look at this, you have this reaction here. Both of them are starting from the same place. This is the conjugated system. Both of them are starting from here. But if you have enough energy, what happens, since both of them also go to the same intermediate, they both go to the same intermediate, that intermediate will be going back and forth. Eventually, it will simply therefore say, okay, since we are going to form the same intermediate, since I have enough energy to do that, I would rather form the more stable product. Okay? So therefore, under higher temperature, the more stable product will be formed. So if you ask me sometime, well, which is the major product? I'll say, well, depending on the condition. Depending on the condition of the reaction. Now, if we are dealing with the thermodynamic product, the more stable product will be formed. But if we are dealing with a kinetically controlled reaction, the product that will be formed will depend on the energy of activation, the rate of the reaction. The product that will be formed in that case will be the one that gives you a lower rate of reaction. Because this here, the 1-2 reaction gives you a lower rate of reaction because the energy of activation is smaller. Okay, is that clear? Okay. Okay, so at this point, I think I want to also, I think we still have a little bit more time. Supposing I give you this. Do one problem here. Okay, I'll give you that. And I ask you, I want to do this reaction. Oh no, I want to change that. That's what I just gave you. No, let's change that. Okay, I have that. And I say, under equilibrium condition, or under thermodynamic condition, which will be the major product of this reaction? Under thermodynamic condition or equilibrium condition, which will be the major product of this reaction? Let me go ahead and number this. This is carbon 1, carbon 2, 3, 4, 5, and 6. Okay. Which will be the major product? Actually, I want to make it just make it a little bit more interesting. Okay. Which will be the major product? Anybody want to give this a try? You almost have to go into the reaction mechanism also. Okay, what is the first thing that will happen in this reaction? What is the first thing that you think will happen? The pi electron attacking the proton, right? Okay. Now, which pi electron will attack the proton? The one on 2? Okay. So if it does that, this pi electron will attack this, right? And of course, this will break this right here. Okay, where would the carbocation be? On 3. Okay, very good, very good. So now you are going to add, that hydrogen is added to here, and as such you have, this here is here. So that means you have a carbocation here, and then you have this here. You have that there. Okay. So at this point you form a tertiary allylic carbocation, right? Okay. So do you expect to get your product from here? You expect to get your product from here? The bromine is still, your bromine is here, right? Does it attack this? Okay. Okay, what happens? Huh? The pi electron will move. Okay. So we want to draw a resonance, right? We want to move this to here. Right. Okay. Let's try. And then we have resonance. So we have this. You say we have this hydrogen that we added. And then the double bond is now here, right? And now we have this here. Now the carbocation is now here. Is that right? Is that right? Okay. So now, at this point, what do you expect to get? We see the bromine here as a nucleophile. What do you expect to get? Well, let's do this way. If the bromine attacks now, right? If it attacks, you get this. Do I have too many bonds here? No, there's no hydrogen here. You guys should have told me that. Okay. 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 So now, that means this is not here. Yes. The one of the pi bond. Where? Don't forget that we added the proton here. This pi bond is still here. This one here? Which one? This here? Oh, the 6 carbon is, oh, okay. It is, oh, yeah, that's, thank you. 1, 2, okay. That would be on this side, right? Oh, I see what happened. 1, 2, 3, okay. Okay. This one here is here, right? Okay, and then this one is still here. And this one is here. Okay. Now, see what is going to happen now. So we now have this here, and now we have this double bond here. Now we have this here, bromine is here. Is that right? Mm-hmm. Okay, that will be a product. And if bromine also, if the bromine attacks this carbon here, what do we get? Okay. So we get these two products. Now the question is, which one of these will be the thermodynamic product? Which one? This here? No. Oh, this one. The one on the right. Okay. Why? Very good. That's correct. Why? Because it is more stable. Exactly. It's because it is more stable. So if you look at this product here, okay? Look at this product here. The double bond is where? It's between this carbon and this carbon. This is what we call a tri-substituted double bond, right? Alkene. This is a tri-substituted alkene. It's a tri-substituted alkene. Keep in mind, we tell you that the thermodynamic product will be the one that is more stable. Okay? So, if these two reactions are allowed to go into equilibrium, if it has enough energy, the major product will be this one here, because this is forming a tri-substituted alkene. As opposed to, what is the substitution on this alkene? What is the substitution on this alkene? Di-substituted alkene. If you recall last semester, di-substituted alkene. So therefore, this here, we will expect this to be the major product if you run this reaction under equilibrium condition, under a thermodynamic condition. Okay. But if you just run this reaction under the kinetic control reaction condition, then it could be this product here. Okay. At that point, the rate of the reaction is what is important. But in this particular instance, if we tell you that this reaction is run under equilibrium condition, in other words, temperature is not a concern, then you have to look for the most substituted product must be the major product. In this particular instance, yes. Equilibrium? Yes. When we say equilibrium, it's the same thing as thermodynamic condition. You guys are packing. Is it time yet? Okay, there will be a short quiz on Thursday based on what we discussed today. Okay, very short quiz on Thursday. I will see you guys on Thursday. Yeah. Oh yes. Now, this one here, okay. Now, depending on what condition you run it, okay. This one could be under a kinetic control condition. This could be, yeah. This could be the product, a major product. Yes.